Materials are the building blocks of the world. Everything from the concrete and steel that hold up this building, to the fabric that the clothes that we wear are made of, to the silicon, the electronic components creating this image, and even including the biological materials like skin, bone, and muscle that hold our bodies together and make them work. And with advances in materials, we can do some pretty amazing things. Like we can build buildings that reach up to a kilometer from the ground. We can build clothes that repel everything from water to fire to bullets. And we can build portable computers, colorful computers that fit in our pockets. And even in the near future, we may be able to print out, synthesize tissues or organs to replace parts of us that are failed. But if we want to keep on coming up with new materials, if we want to keep on finding out new uses for the ones that we have, we need to keep developing our understanding of how materials work. So as an example, I'll use the material I'm working on right now, which is diesel fuel. You might not normally think of it as material, but when I'm doing something like trying to predict its properties or how maybe it flows through a pipe, to me that is very much material science. So how do we make a model of how material works? How do we model how diesel flows through a pipe? So I'm a computational physicist, so I like to start at the most fundamental, general level. How does material work? To do that, we have to go down to the level of protons, neutrons, electrons, where the laws of quantum mechanics reign supreme. And we can usually state them using this equation, the Schrödinger equation, or the equation of quantum. So we put into this equation all the ways in which the electron in the material can interact with each other, with the nuclei in the material, and with their environment. And we solve this equation and get out an energy, which is very important, and another thing which tells us how the electrons are distributed throughout the material. The problem is, it's way easier said than done, because if I wanted to solve it for even, say, 1 trillion of a milliliter of water, which is still about 100 billion atoms, we just could not do it with the computers that we have today. And what's even worse is solving this equation only tells us about one geometry, one way that the nuclei of the material are arranged in space. So if we want to have any hope of simulating how material behaves on a tangible macroscopic scale, we will need to solve this equation many, many times. So it's clear that we need a faster way of getting to that energy. So to see how we might do this, let's take a look at a molecule that you might find in diesel. And let's assume that its total energy is made up of contributions from each of the individual atoms. So you can imagine each atom sort of interacting with its local neighborhood in some way. So the question is, how do we compute that contribution? How do we get that function? One way to do it is to piece together pretty simple functions and tweak those functions until we reproduce experimental data. So that's not a very general approach, and very often it's not as accurate as we need it to be. So the approach that our research group has been developing is to instead systematically derive this approximation from the underlying quantum mechanics. Now the trick that allows us to do that is that similar molecular geometries will in general have similar energies. So what we can do is we can run quantum mechanical calculations on a few geometries, on a small sample of geometries, and then use a clever technique from machine learning to take that information and fill in the energy for any other geometry that we're interested in accurately. So this approach, it works very well for, it's been tested for materials like silicon, germanium, and iron, but there's another whole class of materials where it's not as accurate as we'd like. And the reason is, remember we made this approximation that an atom only sees its local environment. So we can't really account for interactions between atoms that are very widely separated. This is very widely separated in molecular terms. And one such interaction that we're worried about is when atoms like oxygen attract charge to themselves, and then since they're charged objects, repel. So my project is basically to figure out a way to account for and model these interactions. And I'm doing that using another piece of information we get from solving the Schrödinger equation, which is the electron density, which is shown there in blue. And so from that, we can extract this clustering. We can figure out how the charges cluster and what parts of the molecule attract and repel. And we can use our machine learning technique, just like we did with the energy, to fill it in from these individual quantum mechanical calculations to any other geometry that we're interested in. And from there, we can get accurate forces for any geometry. So we're hoping, if this works, that we'll be able to predict the properties of a whole new range of materials. Could be anything from, I don't know, like wet diesel fuel to materials that we don't even know exist yet. So before I close, I'd I'd like to thank my supervisor, Gawar Chani, and everyone else in this research group for lots of helpful and interesting discussions, as well as Shelley for having my PhD, and you, the audience, for listening, especially for the Amanda for organizing this conference.